In our third video of this series, we're going to return to the question from the introduction and finally get at the PDF of the t-statistic defined there. Now, the idea to getting at the PDF of this t-statistic is to treat it as the ratio of two random variables, x and y, for which we already know the distribution. Now, doing so requires a brief amount of algebraic manipulation. If we multiply and divide by sigma, and move the square root of n from the denominator into the numerator, you'll note that the resulting expression can be written as y bar minus mu over sigma root n over s divided by square root of sigma. Now, looking carefully at the term in the numerator, we can see that this is a standard quantity, which we know is a standard normal. We encounter that quite frequently, the distribution of the sample mean. Now in the denominator, you might also recall that in one of the previous videos we showed n minus 1 s squared over sigma is chi squared with n minus 1 degrees of freedom. So while the denominator is not a chi squared, it is basically a chi squared divided by its degrees of freedom. So the t-statistic that we see and that we saw in our application is really a more sort of a specific application of the following general definition. If we have one random variable which is standard normal and a second which is chi-squared with a known degrees of freedom, then we can define a t-distribution as the ratio of x to the square root of y over p. And so any random variable which is defined in this way, we're going to call that a student t-distribution with p degrees of freedom. Now, just a brief note on this name before we move on. The reason why this is called the student t-distribution is because the guy who sort of first popularized the use of this, William Gossett, was an employee of Guinness Beer, as we've sort of mentioned in the past, and that was why we motivated this with Guinness Beer. On another note, this week, at least at the time of the filming of this video, is St. Patrick's Day, so it's a good time to be discussing such things. And apparently, Guinness did not want him publishing under his name, so they made him publish under the pseudonym of Student. Now, I promised earlier in the video that I'd tell you why so many distributions are named after letters, and the honest answer to that is I think it's just because we're lazy mathematicians. We don't want to keep writing shit like this, so we just come up with a letter, in this case T, and attach it to that. But there may be more to it that I'm missing, and if there is, please post it in the comments to this video. Now, the generic form of the PDF of a t-distribution is actually simpler than you'd think. However, I think I'm going to just stick to deriving it in the case where the degrees of freedom is 1. So in that situation, right, we are looking at a ratio of two random variables. Our standard normal, which has density function e to the negative x squared over 2 times 1 over square root of 2 pi. And in the denominator, our chi-squared distribution with 1 degrees of freedom, right, which has density function derived in video 1 over square root of 2 pi y to the negative 1 e to the negative y over 2. And I'll encourage you to go back and check out your work from that video to make sure you know where that came from. So a standard trick in the theory of random variables for deriving the density function of a function of two random variables is to do a bivariate transformation where the first variable u is the one you're interested in. In this case, that's our t-statistic. And the second random variable v, well, it's defined in such a way to kind of make it easier to work with u. So in this case, we're going to define it to be the denominator of u. Now, to see why that's helpful, let's look at the inverse transformations. Because I've defined v to be the denominator of u, I can now write x as a simple product of u times v. And I can write y simply as v squared, which in turn, if I take the Jacobian matrix of that, I'm going to get a pretty simple matrix. So the derivative of x with respect to u is v, the derivative of x with respect to v is u, and then the derivative of y with respect to u is 0, and with respect to v, we get 2v. And that in turn, if I take determinant, gives me simply 2v squared, right? So see, by defining v to be the denominator, we got a fairly simple form for this Jacobian matrix, and we also have a fairly simple form for the inverse transformation. So using our results from the last video, I can look at the joint density function of uv by plugging in x equals uv and y equals v squared into the joint density function of x and y, and then multiplying by the absolute value of the Jacobian, which in this case is already positive. So x and y are independent, therefore their joint density function is the product of their individual density functions, and we'll get 1 over square root of pi e to the negative uv squared over 2, and then times 1 over square root of 2 pi, and now I'm going to plug in v squared for y, so I'll get v to the negative 1 and e to the negative v squared over 2, and then multiplied by my 2v squared. After some slight simplifications, right, we can combine these, we can combine the exponents. I can see that this whole formula can be rewritten as 1 over pi times v, and then the exponent I'm going to have negative u squared plus 1 times v squared over 2. You might be asking me at this point, hey Mayberry, what's the point of this? I thought we wanted the density function of u, and now I have the joint density function of u and v. Well, you'll recall from an earlier course in probability math 131 at Pacific that if you integrate a joint density function, you will obtain the marginal density function for either one of the variables, depending which variable you integrate over. So the marginal for u, for example, I'm going to integrate over the range of possible values of v, which is 0 infinity, and I'm going to look at the integral 1 over pi v e to the negative u squared plus 1 over 2 times v squared dv. And interestingly, this is actually not too bad of an integral to do. Right? You'll notice that with this v out front, the integrand is actually the antiderivative of 1 over u squared plus 1 with a negative sign times e to the negative u squared plus 1 over 2 v squared. So now we just plug in our limits, right? And the result will simplify to 1 over pi, excuse that random mark again, times u squared plus 1. And voila, we have the PDF of a t-distribution with degrees of freedom 1. I encourage you to take a moment to Google online for the more general formula, which can be written in terms of gammas and powers, which depend on the degrees of freedom. But this will suffice for our applications, or at least our understanding of the applications. Now, to conclude this video, I just wanted to give you a brief PDF comparison to kind of come back to one of the ideas we put in the introduction, which is how does the t-distribution compare with the standard normal? So in this chart here, the standard normal curve is in black, and then I've plotted two different t-distributions, the first in orange with degrees of freedom 1 and the second in blue with degrees of freedom 10. So you can see that the tails of the degrees of freedom 1 t-distribution, the orange curve, are much fatter than either of the other, and that the tails of the degrees of freedom 10 are also much fatter than the standard normal curve. So what happens is as the degrees of freedom goes to infinity, df goes to infinity, the t-distribution, this can be shown, actually does converge to the standard normal. Right? But for smaller sample sizes, you actually will decrease the type 1 error rates by using this t-distribution instead of the z, right? Because you'll be choosing different cutoffs for your tests than you would under the standard normal distribution. So in the last video, we're going to come back and give an example of how to do a hypothesis test using everything we've done. It'll be a relatively short and easy one, hopefully a fun application, and that will conclude this video series once and for all.